In this video, I wanted to show you some examples of using the log laws to either simplify or rewrite logarithmic expressions. A common type of question you could be asked in your homework or something would be to either combine logs or expand logs using the laws of logarithms. So let's just look at a few examples. So what it says is use log laws to simplify or alter the following. But like for the very first one in the packet, we could always take two logarithms and combine them together. And that's, what the directions might say in these first couple examples is combine the following logarithmic expressions. And basically, what I need to first determine is which log law am I going to be using. Like for here, since I have log of 5 plus log of 2, I would use number 1, because number 1 tells me if I have log plus log, that it will be equal to log of AB. And so I could kind of imagine each of those as, well, this is like my capital A. Whoops, don't have my pen out. There we go. Log capital A, and this is capital B. And so what that should be equal to is log of A times B, or log of 5 times 2, which was, of course, 10. And what's always important is that the base of the logarithms must be the same, and then the new logarithm that you're creating here is also going to be the same base. Here, since there is no base, well, there always must be a base, but just like with a square root, you don't write the 2 in the index. When there is no base presented, that's always base 10, the common log. Well, actually, I talked about the common log in a previous video, but in certain mathematical sources, they actually use base E as the common log base. It's kind of irritating because most algebra and mathematical textbooks, they use base 10 to be common log. And in terms of this course, you can always assume the common log is base 10 because we have the natural log for base E, and it's, anyways. But the log base 10, since this is base 10, and remember one of the other basic properties of logarithms is that when the base matches the input, that's always going to produce 1. I don't know why I'm doing this in red. I'll go ahead and rewrite it in black. Because a logarithm tells us, well, what power do I need to take the base to get the input? And of course, to take 10, I could raise it to the first power to get 10. And that's why we get log 1. But of course, we could always use a calculator to evaluate it as well. But that's not the point of these examples. The point of these examples is to see, well, how do I combine 2 logs into 1? It always works in a multiplicative fashion. What's also interesting to note is I could look at the logarithms individually, like what is the log of 5 and what is the log of 2? And by these log laws, I could think about ways of combining these weird things together. Because again, the log of 5 would represent what power I need to take 10 to get to 5. That's going to be kind of awkward because 10 does not exponentiate to get 5 in any easy way. And same with 2, 10 does not exponentiate well to get to 2. But if I look at those answers given by my calculator, I can see that if I add those two things together, 0.698 plus 0.301, that would give me exactly 1. And of course, that's a little bit more obvious when using the laws of logarithms, because they combine into exactly the base at the end of the day. But basically, it's a way of transitioning 2 logs to 1. Same thing for subtraction. If we have the subtraction of 2 logarithms, again, I could look at this as like A and B. What would happen is that would turn into a singular logarithm of the same base of A divided by B. So since here we have the natural log of 69 minus the natural log of 3, this would combine into the natural log of the first divided by the second. Of course, I could simplify that to 20, because 69 divided by 3 is just 23. And that would give me now a singular log. And you may be wondering, well, this one's not as obvious because the natural log is base E, and E doesn't exponentiate in any obvious fashion to get to 23. But, with these sorts of questions in your homework, usually it's going to be looking for the answer expressed exactly as a logarithm. Of course, you could go into a calculator to figure out what that is, but that's kind of defeating the point of the problem. The point of the problem is to rewrite the expression, not to get the answer. Because the answer, you could have just typed those in to begin with to see what is the ln of 69 minus the ln of 3. It's 3.13. But of course, it's sort of like simplifying. It's sort of like in algebra when we, when we have the square root of 8, we could rewrite that as 2 root 2. It's sort of a way of breaking down a number into its components and writing it in a different form. With logarithms, they can always be joined together, assuming they have the same base. And actually, logarithms of different bases can be combined as well by using change of base. And so there are processes for doing that, not really worth our brain power to do those. But in the same way, you could use these log laws in reverse as well, because in these examples, I took two different logarithms and I combined them into one. You could also, sometimes it might tell you to expand a logarithm or write it as a sum of multiple different logarithms. And again, these problems, they don't have specific instructions, so they're kind of like a concept map where I'm just giving you some examples and showing you ways you can play around with them. So these questions aren't like your normal math questions where it's like a goal, we're trying to do something specific. I just wanted to show you how these work. So with the natural log of 4, and this is sort of the thing is, well, what do I do? I can't, I could solve this with a calculator, but it's just the natural log of a number. Well, we could always think of a way of factorizing a logarithm. Like, for example, 4 is equal to 2 times 2. So I could rewrite ln of 4 as the natural log of 2 times 2. And why might I want to do it that way? It's because, well, if I can take a number and factor it, I could break it down into 2 separate logarithms, right? Because what we know is if I have the log of a times b, that will break down to the log of a plus the log of b. And since 4 is factorable as 2 times 2, I could change this to the natural log of 2 plus the natural log of 2 by log law number 1. And in this particular case, that's actually just equal to, since this is the same thing plus itself, twice the natural log of 2. And again, it's a way of expanding a single logarithm, changing it into multiple logarithms. And usually if you're asked to do this, it would say something along the lines of expand this logarithm and write it as multiple logarithms or something to that extent. Or a totally different way of looking at this is the ln of 4 is also equal to the ln of 2 squared, because you could also think of the number within a logarithm as an exponential expression. And if we were to then apply log law number 3, log law number 3 states that if I have an exponent within a logarithm that's equal to that you can always extract the exponent out front and write it as a multiplier. C times logarithm. And looking at it this way, I can, if I think about 4 as an exponential expression, I could think about that as ln of 2 squared, and I could drop that exponent out front by log law number 3, which would leave me with 2 ln of 2, but notice I get the same thing. And this brings up another important point about these laws, is that they can all seem very different and kind of odd and strange sometimes, but they all work together. They're always going to make sense. And there's not necessarily a correct order that you can apply them. They can all be applied, and you should get the same simplification or alternate expression, no matter how you go about it. And there's a lot of different forms you can write them in. And same thing with log of 81. If I was to write that, as I could write that as log of 9 squared, and that would leave me with 2 log 9 as an alternate way of writing it. But additionally, you could write 81 as 3 to the 4th power, because 9 is 3 squared, so I could think about it as 3 squared squared, so that should also be equal to 4 times the log of 3. And basically there's alternate ways, alternate forms of going about logarithms, and this is sort of like simplifying an expression. It's very similar, like I like to think of it about it much like a square root. Like, say you have the square root of 4 that's equal to 2. I can use particular properties of the numbers to simplify it, and if I see particular powers within that logarithm, I can always extract them using log law number 3. I'll continue with more examples in the next video.